Air conditioning is the process of altering the properties of air to more comfortable conditions, typically with the aim of distributing the conditioned air to an occupied space such as a building or a vehicle to improve thermal comfort and indoor air quality. In common use, an air conditioner is a device that lowers the air temperature. The cooling is typically achieved through a refrigeration cycle, but sometimes evaporation or free cooling is used. Air conditioning systems can also be made based on desiccants. In the most general sense, air conditioning can refer to any form of technology that modifies the condition of air humidification, cleaning, ventilation, or air movement. However, in construction, such a complete system of heating, ventilation, and air conditioning is referred to as heating, ventilation, and air conditioning. History. The basic concept behind air conditioning is said to have been applied in ancient Egypt, where reeds were hung in windows and were moistened with trickling water. The evaporation of water cooled the air blowing through the window. This process also made the air more humid, which can be beneficial in a dry desert climate. In ancient Rome, water from aqueducts was circulated through the walls of certain houses to cool them. Other techniques in medieval Persia involved the use of cisterns and wind towers to cool buildings during the hot season. Modern air conditioning emerged from advances in chemistry during the 19th century, and the first large-scale electrical air conditioning was invented and used in 1902 by American inventor Willis Carrier. The introduction of residential air conditioning in the 1920s helped enable the Great Migration to the Sun Belt in the United States. Development of mechanical cooling. The 2nd century Chinese inventor Ding Yuan of the Han Dynasty invented a rotary fan for air conditioning, with 7 wheels 3 meters in diameter and manually powered. In 747, Emperor Xuanzong of the Tang Dynasty had the Cool Hall built in the imperial palace, which the Tang Yuan describes as having water-powered fan wheels for air conditioning as well as rising jet streams of water from fountains. During the subsequent Song dynasty, written sources mentioned the air conditioning rotary fan as even more widely used. In the 17th century, Cornelis Drebbel demonstrated turning summer into winter for James I of England by adding salt to water. In 1758, Benjamin Franklin and John Hadley, a chemistry professor at Cambridge University, conducted an experiment to explore the principle of evaporation as a means to rapidly cool an object. Franklin and Hadley confirmed that evaporation of highly volatile liquids could be used to drive down the temperature of an object past the freezing point of water. They conducted their experiment with the bulb of a mercury thermometer as their object and with a bellows used to speed up to the evaporation. They lowered the temperature of the thermometer bulb down to -14 degrees Celsius while the ambient temperature was 18 degrees Celsius. Franklin noted that, soon after they passed the freezing point of water 0 degrees Celsius, a thin film of ice formed on the surface of the thermometer's bulb and that the ice mass was about a quarter-inch thick when they were stopped the experiment upon reaching -14 degrees Celsius. Franklin concluded, "From this experiment one may see the possibility of freezing a man to death on a warm summer's day." In 1820, English scientist and inventor Michael Faraday discovered that compressing and liquefying ammonia could chill air when the liquefied ammonia was allowed to evaporate. In 1842, Florida physician John Gorrie used compressor technology to create ice, which he used to cool air for his patients in his hospital in Apalachicola, Florida. He hoped to eventually use his ice-making machine to regulate the temperature of buildings. He even envisioned centralized air conditioning that could cool entire cities. Though his prototype leaked and performed irregularly, Gorrie was granted a patent in 1851 for his ice-making machine. His hopes for its success vanished soon afterwards when his chief financial backer died. Gorrie did not get the money he needed to develop the machine. According to his biographer, Vivian M. Sherlock, he blamed the Ice King, Frederick Tudor, for his failure, suspecting that Tudor had launched a smear campaign against his invention. Dr. Gorrie died impoverished in 1855, and the idea of air conditioning went away for 50 years. Since prehistoric times, snow and ice were used for cooling. The business of harvesting ice during winter and storing for use in summer became popular towards the late 19th century. This practice was replaced by mechanical ice-making machines. James Harrison's first mechanical ice-making machine began operation in 1851 on the banks of the Barwon River at Rocky Point in Geelong. His first commercial ice-making machine followed in 1854, and his patent for an ether vapor compression refrigeration system was granted in 1855. This novel system used a compressor to force the refrigeration gas to pass through a condenser, where it cooled down and liquefied. The liquefied gas then circulated through the refrigeration coils and vaporized again, cooling down the surrounding system. The machine employed a 5 meters flywheel and produced 3,000 kilograms of ice per day. Though Harrison had commercial success establishing a second ice company back in Sydney in 1860, he later entered the debate over how to compete against the American advantage of unrefrigerated beef sales to the United Kingdom. He wrote, "Fresh meat frozen and packed as if for a voyage, so that the refrigerating process may be continued for any required period," and in 1873 prepared the sailing ship Norfolk for an experimental beef shipment to the United Kingdom. His choice of a cold room system instead of installing a refrigeration system upon the ship itself proved disastrous when the ice was consumed faster than expected. Electromechanical cooling. In 1902, the first modern electrical air conditioning unit was invented by Willis Carrier in Buffalo, New York. After graduating from Cornell University, Carrier found a job at the Buffalo Forge Company. While there, he began experimenting with air conditioning as a way to solve an application problem for the Sackett-Wilhelms Lithographing and Publishing Company in Brooklyn, New York. The first air conditioner, designed and built in Buffalo by Carrier, began working on the 17th of July 1902. Designed to improve manufacturing process control in a printing plant, Carrier's invention controlled not only temperature but also humidity. Carrier used his knowledge of the heating of objects with steam and reversed the process. Instead of sending air through hot coils, he sent it through cold coils. The air was cooled, and thereby the amount of moisture in the air could be controlled, which in turn made the humidity in the room controllable. The controlled temperature and humidity helped maintain consistent paper dimensions and ink alignment. Later, Carrier's technology was applied to increase productivity in the workplace, and the Carrier Air Conditioning Company of America was formed to meet rising demand. Over time, air conditioning came to be used to improve comfort in homes and automobiles as well. Residential sales expanded dramatically in the 1950s. In 1906, Stuart W. Kramer of Charlotte, North Carolina was exploring ways to add moisture to the air in his textile mill. Kramer coined the term air conditioning, using it in a patent claim he filed that year as an analog to water conditioning, then a well-known process for making textiles easier to process. He combined moisture with ventilation to condition and change the air in the factories, controlling the humidity so necessary in textile plants. Willis Carrier adopted the term and incorporated it into the name of his company. Shortly thereafter, the first private home to have air conditioning was built in Minneapolis in 1914, owned by Charles Gates. Realizing that air conditioning would one day be a standard feature of private homes, particularly in regions with warmer climate, David Street, Pierre Dubos designed a network of ductwork and vents for his home Meadowmont, all disguised behind intricate and attractive Georgian-style open moldings. This building is believed to be one of the first private homes in the United States equipped for central air conditioning. In 1945, Robert Sherman of Lynn, Massachusetts invented a portable, in-window air conditioner that cooled, heated, humidified, dehumidified, and filtered the air. The idea was subsequently stolen by a large manufacturer. Sherman did not have the resources to fight the big corporation in court and thus never received any money or recognition. He died in 1962. Refrigerant development. The first air conditioners and refrigerators employed toxic or flammable gases, such as ammonia, methyl chloride, or propane, that could result in fatal accidents when they leaked. Thomas Midgley, Jr., created the first non-flammable, non-toxic chlorofluorocarbon gas, Freon, in 1928. The name is a trademark name owned by DuPont for any chlorofluorocarbon, hydrochlorofluorocarbon, or hydrofluorocarbon refrigerant. The refrigerant names include a number indicating the molecular composition. The blend most used in direct expansion home and building comfort cooling is an HCFC known as chlorodifluoromethane. Dichlorodifluoromethane was the most common blend used in automobiles in the U.S. until 1994, when most designs changed to R134A due to the ozone-depleting potential of R12. R11 and R12 are no longer manufactured in the U.S. for this type of application, so the only source for air conditioning repair purposes is the cleaned and purified gas recovered from other air conditioner systems. Several non-ozone depleting refrigerants have been developed as alternatives, including R410A. It was first commercially used by Carrier Corp. under the brand name Puron. Modern refrigerants have been developed to be more environmentally safe than many of the early chlorofluorocarbon-based refrigerants used in the early and mid-20th century. These include HCFCs and HFCs have replaced most CFC use. HCFCs, in turn, are supposed to have been in the process of being phased out under the Montreal Protocol and replaced by HFCs such as R410A, which lack chlorine. HFCs, however, contribute to climate change problems. Moreover, policy and political influence by corporate executives resisted change. Corporations insisted that no alternatives to HFCs existed. The environmental organization Greenpeace solicited a European laboratory to research an alternative ozone and climate-safe refrigerant in 1992, gained patent rights to a hydrocarbon mix of isopentane and isobutane, but then left the technology as open access. Their activist marketing first in Germany led to companies like Whirlpool, Bosch, and later LG and others to incorporate the technology throughout Europe, then Asia, although the corporate executives resisted in Latin America, so that it arrived in Argentina produced by a domestic firm in 2003, and then finally with giant Bosch's production in Brazil by 2004. In 1995, Germany made CFC refrigerators illegal. DuPont and other companies blocked the refrigerant in the U.S., with the U.S. EPA disparaging the approaches that German technology. Nevertheless, in 2004, Greenpeace worked with multinational corporations like Coca-Cola and Unilever, and later PepsiCo and others, to create a corporate coalition called Refrigerants Naturally. Then, 4 years later, Ben & Jerry's of Unilever and General Electric began to take steps to support production and use in the U.S. Only in 2011 did the EPA finally decide in favor of the ozone and climate-safe refrigerant for U.S. manufacture. Operating principles. Refrigeration cycle. In the refrigeration cycle, heat is transported from a colder location to a hotter area. As heat would naturally flow in the opposite direction, work is required to achieve this. A refrigerator is an example of such a system, as it transports the heat out of the interior and into its environment. The refrigerant is used as the medium which absorbs and removes heat from the space to be cooled and subsequently rejects that heat elsewhere. Circulating refrigerant vapor enters the compressor and is compressed to a higher pressure, resulting in a higher temperature as well. The hot, compressed refrigerant vapor is now at a temperature and pressure at which it can be condensed and is routed through a condenser. Here it is cooled by air flowing across the condenser coils and condensed into a liquid. Thus, the circulating refrigerant removes heat from the system and the heat is carried away by the air. The condensed and pressurized liquid refrigerant is next routed through an expansion valve where it undergoes an abrupt reduction in pressure. That pressure reduction results in flash evaporation of a part of the liquid refrigerant, lowering its temperature. The cold refrigerant is then routed through the evaporator. A fan blows the warm air across the evaporator, causing the liquid part of the cold refrigerant mixture to evaporate as well, further lowering the temperature. The warm air is therefore cooled. To complete the refrigeration cycle, the refrigerant vapor is routed back into the compressor by placing the condenser inside a compartment, and the evaporator in the ambient environment, or by merely running an air conditioner's refrigerant in the opposite direction. The overall effect is the opposite, and the compartment is heated instead of cooled. See also heat pump. The engineering of physical and thermodynamic properties of gas-vapor mixtures is called psychrometrics. Heat pump unit. A heat pump is an air conditioner in which the refrigeration cycle can be reversed, producing heating instead of cooling in the indoor environment. They are also commonly referred to as a reverse cycle air conditioner. The heat pump is significantly more energy efficient than electric resistance heating. Some homeowners elect to have a heat pump system installed as a feature of a central air conditioner. When the heat pump is in heating mode, the indoor evaporator coil switches roles and becomes the condenser coil, producing heat. The outdoor condenser unit also switches roles to serve as the evaporator, and discharges cold air. Air source heat pumps are more popular in milder winter climates where the temperature is frequently in the range of 40 to 55 degrees Fahrenheit, because heat pumps become inefficient in more extreme cold. This is because ice forms on the outdoor unit's heat exchanger coil, which blocks airflow over the coil. To compensate for this, the heat pump system must temporarily switch back into the regular air conditioning mode to switch the outdoor evaporator coil back to being the condenser coil, so that it can heat up and defrost. A heat pump system will therefore have a form of electric resistance heating in the indoor air path that is activated only in this mode in order to compensate for the temporary indoor air cooling, which would otherwise be uncomfortable in the winter. The icing problem becomes much more severe with lower outdoor temperatures. So heat pumps are commonly installed in tandem with a more conventional form of heating, such as a natural gas or oil furnace, which is used instead of the heat pump during harsher winter temperatures. In this case, the heat pump is used efficiently during the milder temperatures, and the system is switched to the conventional heat source when the outdoor temperature is lower. Absorption heat pumps are a kind of air source heat pump, but they do not depend on electricity to power them. Instead, gas, solar power, or heated water is used as a main power source. An absorption pump dissolves ammonia gas in water, which gives off heat. Next, the water and ammonia mixture is depressurized to induce boiling, and the ammonia is boiled off, which absorbs heat from the outdoor air. Some more expensive window air conditioning units have a true heat pump function. However, a window unit may only have an electric resistance heater. Evaporative cooling in very dry climates. Evaporative coolers, sometimes referred to as swamp coolers or desert coolers, are popular for improving coolness during hot weather. An evaporative cooler is a device that draws outside air through a wet pad, such as a large sponge soaked with water. The sensible heat of the incoming air, as measured by a dry bulb thermometer, is reduced. The total heat of the entering air is unchanged. Some of the sensible heat of the entering air is converted to latent heat by the evaporation of water in the wet cooler pads. If the entering air is dry enough, the results can be quite substantial. Evaporative coolers tend to feel as if they are not working during times of high humidity, when there is not much dry air with which the coolers can work to make the air as cool as possible for dwelling occupants. Unlike other types of air conditioners, evaporative coolers rely on the outside air to be channeled through cooler pads that cool the air before it reaches the inside of a house through its air duct system. This cooled outside air must be allowed to push the warmer air within the house out through an exhaust opening such as an open door or window. These coolers cost less and are mechanically simple to understand and maintain. An early type of cooler, using ice for a further effect, was patented by John Gorrie of Apalachicola, Florida in 1842. He used the device to cool the patients in his malaria hospital. Free cooling air conditioning can also be provided by a process called free cooling, which uses pumps to circulate a coolant from a cold source, which in turn acts as a heat sink for the energy that is removed from the cooled space. Common storage media are deep aquifers or a natural underground rock mass accessed via a cluster of small diameter boreholes, equipped with heat exchanger. Some systems with small storage capacity are hybrid systems, using free cooling early in the cooling season, and later employing a heat pump to chill the circulation coming from the storage. The heat pump is added because the temperature of the storage gradually increases during the cooling season, thereby declining its effectiveness. Free cooling systems can have very high efficiencies, and are sometimes combined with seasonal thermal energy storage, so the cold of winter can be used for summer air conditioning. Free cooling and hybrid systems are mature technology.